Hello everyone, in this video we are going to present our third year robotics project as part of our engineering degree program at UniLaSalle Amiens. So, my name is Georges-Henri.
And my name is Aymeric. In this presentation, we are going to start to describe the various parts we had to build the robot. Then we are going to explain how we assembled it. And finally, we are going to explain the code parts of our project.
To carry out this project, various materials were made available to us based on compatibility with the Arduino environment, system responsiveness, and ease of integration into a compact chassis. Among the materials we used two FS90 R servo motors used for the movement of the robot and controlled via pulse width modulation PWM signal, allowing continuous rotation of the robot in both directions. They are very often used in miniature robotics projects and electronic hobby applications, especially those involving microcontrollers like Arduino, for example. Power with a 5-volt supply. Another particular feature of the servo motors is that it's easy to use due to its small size and has a very affordable cost. Next, we use three VL61HEX sensors placed respectively on the left, center, and right to accurately detect distances in front of the robot. These sensors measure distance using time-of-flight technology, which calculates the flight time of a reflected light signal. They offer reliable accuracy for distances under 20 cm and communicate via the I2C bus. However, an important characteristic must be taken into account. All VL61HEX sensors share the same default I2C address, which makes the simultaneous use impossible without modification. To solve this problem, in the robots program, we assign each sensor a unique address. Finally, at the very heart of our project, we use a Meccano board that acts as the brain and control center of the robot. It collects and processes distance data from the three VL61HEX sensors for obstacle detection and generates PWM signals to precisely control the speed and direction of the two servo motors. In addition to those mentioned above, we also use, among other things, a chassis which represents the basic structure serving as a support for the other components, two wheels for the effective movement of the robot, a battery for its power supply, a pololo ball caster, and a power cord. For the assembly of the robot, we mounted the components onto a chassis at the predefined space. For the Arduino board, it goes onto the child and then in the middle of the chassis. It is the core of the robot, where the servo motors and the sensors are wide. To allow the board to work on the circuit, we added a battery that goes inside the chassis. To link these two, we use a cable that we had to intertwine with the chassis to avoid it to disrupt the trajectory. For the wheels, they go on the left and right backside of the chassis, directly attached on the axis of the servo motors with a screw. In addition, we have mounted the pololo ball caster in the front of the chassis to stabilize the robot and avoid that it slides along the floor. For the servo motors, there is three wires, a red which is for the alimentation, an orange which is for the PWM signal, and a brown which is for the count. To link the latter to the Arduino board, we use the corresponding pin for the alimentation and the count. However, for the signal, we had to use a number pin with a wave next to the number, which means that the pin is able to manage pulse-wide modulation signal.
For the sensors, there is 5 pins that we have to use. The VIN pin, which is for the alimentation, the GND pin, which is for the ground, the SDA pin, which is for the transfer of data between the sensor and the board, the SCL pin, which is for the clock signal and synchronize the data transfer, and the JPIO0CE pin, which is for the definition of the I2C address, putting them according to the display diagram. Once our robot was assembled, we started to learn how to code with Arduino. We learned that Arduino works with 2 major functions. The function setup, which is run once at the very beginning, and is used to initialize the function of the Arduino board pin, which are input or output, or the various components. And the other function is the function loop, that is run continuously, and in our case is used to monitor the movement of the robot. In our project, we use 3 Arduino libraries. The first one is servo.h, which is useful for controlling the servo motors. The second is wire.h, which is useful to manage the E2C communication between the time-of-flight sensor that we use and the Arduino board. And the last one is VL6180X.h, which is useful to use the sensors. For the description of the code, I am going to subdivide the presentation into 4 subparts. I'm going to start with the header, then the setup, the loop, and finally I'm going to explain some of our functions. So for the header, we start to call for the various libraries described previously, then we define some macro that will be useful to clarify the code. For example, we define threshold front and threshold side, which correspond to the minimal distance we want respectively on the front and the side of the robot before it should take actions. In the setup function, we initialize the various components of the robot. We start with the servo motors, with the function attach, defined in the servo.h library. This function binds a pin of the Arduino board with the servo motor to allow the board to send a PWM signal. Then we do the same for the sensors with the default function from Arduino, pin mode. However, for the sensors it is not enough. We have to use several other functions in order to initialize them. They all come from the VL6180X.h library. In the loop function, we manage the movement of the robot. We start by reading the value of the sensors to decide what actions the robot should do. For example, if the distance in front of the robot is less than a certain threshold, defined in the header, then we know that the robot will have to turn. To know the direction of the turn, we compare the value read by the left sensor with the value from the right sensor. So if the first is greater than the others, the bot will have to turn left and vice versa. Now I am going to explain the role of our most useful functions. The function forward and backward makes the robot move in the direction of the name. As we can see, the angle is different for the 2 motors. It is because they are mounted in mirror with one another. You could have increased the speed of the robot. However, we have decided to keep it relatively low so that the robots have time to detect the walls of the labyrinth. The function turn left and turn right, which makes the robot do the eponymous movement. The operation is relatively simple. While the motor continues to work normally, we reduce the speed of the other, thus making the robot turn. The function delay is here to avoid that the robot stops in the middle of the turn.
In conclusion, this project has brought us a lot. whether it is through the numerous knowledge developed or even cohesion with our comrades. It was therefore a good introduction to electronics that was both fun and interesting. We encountered several problems. For example, we had a lot of trouble connecting the components to the Arduino board because it required us to be very meticulous, and many times the wire detached and even broke, thus requiring us to change them and restart the connection.
Another example of the problems we encountered is the behavior of sensors with respect to brightness and different surfaces. Indeed, during the test we carried out, we did not understand the reason why the sensors were indicating outliers. We thought that these were defective. However, the real problem is that the type of sensor used is very sensitive to the parameter mentioned earlier, which distorts the returns measurement and leads to robot behavior errors that have left us confused more than once. Finally, our robot completed the circuit in 36 seconds. It is not the real pride, but at least we managed to do something. There are of course some points that we could improve. For example, further optimizing the code or ensuring that the sensors are in the best possible conditions for their operation. Thank you.